Okay, and we're going to start.
Did you guys get my email? I sent out an email from Jupiter Graves. Okay. Be checking that and consistently be checking and making sure that I'm getting it. So at the moment, only attendance and the quiz is on it. But so make sure that I have you marked as present when you're present and all that good stuff. Okay. We're going to be continuing with functions. So we're still in section 1.1. It's a very long section because we have to be reminded a lot about functions here. And we're going to move on to talking about domains. So we're still in 1.1. And we're going to talk about domains of functions. Anyone tell me what they think domain is? Yeah?
Well, the X value.
Not just the X values, you want to kind of think of it as a set. So it's a set of X values, or more in general, think of it as inputs. Because again, remember, X and Y are kind of dummy variables. We might call it X's, we might call it something else. So a set of inputs for which a function is defined. You can also think of it as where a function makes sense. Or where a function works. Right, so it's the set of values that you can plug into a function and the function will work. By this way means let's define what I mean. What does it mean the function works? It means the function gives a meaningful answer. Meaningful in the way we'll be using it in this class is it gives you a real number as the output. Okay? So 1 over 0 is not a meaningful answer. So any function that outputs 1 over 0 means it's gibberish. Okay? But the set of values that we can plug into a function and it will give us some meaningful answer, we call that set the domain, the set of inputs. Right? And one, domains may be given, right? So for example, I can actually give you a function, say f of x equals 2x plus 3, and then I can actually say for x between 1 and 3, not including 1, including 3, right? So you can be given this information. Right? So sometimes you give a definition, but you don't want it to work always or everywhere, so you can specifically say to the audience, okay, here's where this function that I'm defining will work. It will work for all these values. So if I give you x equals 4, I don't know what that will be. It doesn't make sense. It's not defined for values of x equals 4, so it's not in the domain. Right? So I can say this is a function that is defined on this domain. It means those are the values that it would make sense to plug into the function. Okay? Another way you can determine domains is sometimes domains may be determined by the nature of the functions themselves. That's in the case where no restriction is given. No one tells you a restriction, they just say, here's a function. And the function will tell you what the domain is based on the function. And it's hard to describe that one in general, but with the functions we will commonly be using in this class, we actually know a lot about their domains. So I'm going to talk about a few specific ones, and we'll actually talk about some later on. So let's look at some important functions. First kind of important function that we need to know about are called polynomials. So in this class we will talk about several kinds of functions: polynomials, rational functions, radical functions, exponential functions, logarithmic functions. Exponential functions and log functions I'm not going to talk about today, they'll come later, but I need to tell you about the first three, and more specifically how to determine the domain of the first three, because that will be important. So these are functions. Okay, anyone tell me what a polynomial looks like? Anyone give me an example of a polynomial? It's an example of a polynomial function.
Those are ones that are like 5x5 minus 4x3, like we just have a bunch of exponents, basically.
Yeah, exactly. So these are functions of this form. So f of x equals, or y equals, or something equals a n x to the n plus a n minus 1 x to the n minus 1, and they can count down, where the ai's are constants and n is a non-negative whole number. So anything that looks like this, where your n can be 0 or 1 or 2 or 3 or 4, that we call a polynomial. And these guys are called the coefficients of the polynomial. A n would be called the leading coefficient, the number in front of the x with the highest power is called the leading coefficient. So for example, y goes like she was saying, 5x to the fifth plus 4x cubed minus 7 is an example of a polynomial, or y equals x squared plus x is an example of a polynomial. Order doesn't matter, so I could put the number in front and then x's come after. That's also a polynomial. Things that are not polynomials. So something like y equals x to the 1/2 plus 2x is not a polynomial. Y equals 5x plus 3x squared minus 7x to the minus 1. Why is this not a polynomial? What rule did it break? Yeah?
It's not a whole exponent.
Here's a power, and it's a half. It's not a whole number exponent. Okay? What about this one? Yeah?
There's the negative 1 exponent.
That's not a polynomial because of x to the minus 1. Okay? That has a negative exponent, we have to be non-negative. Non-negative means greater than or equal to 0. Okay? And it's important to be able to distinguish these kinds of functions because they behave very differently, especially in terms of domains. The domains of something like this are very different from the domains of functions like this. So it's very important that you remember, not just learn, because I would think you guys have seen this before, but remember how to distinguish these functions and then talk about them. So when you're talking about domains of polynomials, okay, in general, unrestricted, let's say I don't force you to stick to a certain region. What is the domain of a polynomial? What are the set of numbers that I can plug into the polynomial and it will work? Give me a meaningful answer. Yeah?
1 and higher as long as it's a whole number.
Only 1 and higher? What if I plugged in minus 1 for x here? Would that give me a meaningful answer? Yeah?
Isn't it negative infinity to infinity?
It's negative infinity to infinity, all real numbers. Right? So it's not just like 1 or higher or restriction. That might be a domain of another function. But any polynomial, as long as I do not restrict the domain, literally you can plug in anything. Anything on the number line will work in a polynomial. It will give you an answer. It could be negative, could be positive, could be 0, could be a fraction, could be a decimal. It doesn't matter. It will work if I plug it to the polynomial. You can notice that the examples I gave here that is not the case. For example, I cannot plug in 0 into this one, right? Because x to the minus 1 is 1 over x, and plugging in 0 is divided by 0. I could not plug in, say, minus 4 into this one, right? Because x to the half is square root of x. You can't take the square root of minus 4. It's not meaningful, okay? So that's not true for other kinds of functions. But for a polynomial, you can literally plug in any number you want, anything on the number line. And you write that in this way. This is interval notation. So this is basically saying that your x can be any number between negative infinity and infinity, the entire number line. Right? So polynomials are very nice functions in this regard. They work everywhere. Right? Not all functions are that nice. In fact, very few functions are as nice as polynomials. In fact, well, we won't see it in this class, but in fact, in higher classes, we figure out ways to write other functions to look like polynomials in order to get some of these nice properties. You call those power series, but that's not in this class. We'll not talk about that. But polynomials are very nice. They work everywhere. The domains of a polynomial is all real numbers, unless I specifically tell you I'm forcing you to be restricted somewhere. Another kind of important functions are what we call radical functions. These are functions of the form something like y equals a radical x, where there's a number in front of here. Right, so examples would be like y equals the square root of x, or y equals the cube root of x, or something like y equals x to the 2/3, etc. Right? These are examples of radical functions. Right, these are basically, it's kind of like polynomials, except the powers are fractions. They're not whole numbers. Okay? And they behave a very specific way. So, what about the domains of these guys? You can tell me where a radical works, yes?
Is it 0 to infinity?
Is that true? Yeah?
Well, doesn't it depend what the radical is?
In what sense?
It can't, for square root, you can't have a negative, but for a cube root, you can.
Yes, so you will have half the answer. The answer is it depends on what that number n is. Okay? So if you're talking about the domain of the nth root of x, there are two possibilities. It will only be from 0 to infinity, 0 or bigger, if n is even. That means n is 2, 4, 6, 8, 10, 12, blah, 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 right? Notice that when n is 2, you actually don't write it. So this actually means n is 2. However, if n is odd, this means if n looks like 1, 3, 5, 7, 9, blah, 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 it actually works everywhere. So you can take the cube root of a negative number, right? The cube root of minus 8 is minus 2. Multiply minus 2 by itself 3 times, you get minus 8, right? You can't take the square root of minus 4 because you multiply 2 by itself, you get positive 4. You multiply minus 2 by itself, you get positive 4. You can't, that negative 4 escapes you. There are things called complex numbers where this works, but this is not in the scope of this class, so we're not going to worry about this. As far as we're concerned, for an even radical to work, the number underneath must be positive or 0. Okay, it can be 0, square root of 0 is 0, but it has to be bigger if this number is even. If it's odd, it doesn't matter, it works everywhere. Okay? That's another very important kind of function. And its domain. You guys got this, right? Another important kind of function is the so-called rational function. Now this doesn't mean the function is reasonable or intelligent or well-mannered or anything like that. What does a rational function mean? Does anyone know what a rational function is? Yeah?
Is it if there's two polynomials on top?
Exactly. Rational actually comes from the root word ratio, which means you're dividing things. So these are functions of the form your y is equal to p of x divided by q of x, where p and q are polynomials. So the first kind of function I talk about. So if I take two polynomials and I divide one by the other, I get what we call a rational function. What about the domain of a rational function? Yeah?
It's based on the denominator, so like the denominator can equal 0.
Okay, so remember that last move we spoke about in this class is very super important. Every time you see a ratio, a math person always worries about, what about the denominator? Is it ever 0? You have to avoid divided by 0. And that defines the domain of a rational function. The domain is all real x such that q of x not equal to 0. And q of x here, of course, refers to the denominator. The denominator cannot be 0 in a rational function. So if you want to find the domain of a rational function, you take the bottom, set it equal to 0, solve for all those x values, and you have to avoid those x values. Yes, so let's actually do some examples now, where we actually find domains. Find the domains of the following. A. G of x equals 3 divided by x equals 2. B. I have a few more examples, but we'll get to this later. Let's find the domain of these, the domains of these functions. You might also notice that in the quiz, in the bonus section of the quiz, I asked you about domains. Now this is going to be typical. So what on the quizzes, when I put a bonus section, these are like extra. So the quiz really, the overall grade is computed based on what's before, and then the bonus is like extra points that you can get extra credit. So the idea is technically you can get more than 100% on a quiz, but I'll just take that extra that you get and add it to another quiz. So that's a bonus. And really the bonuses will be based on topics that I have yet to cover in class. So if I'm about to cover something, on the quiz I'll put a bonus on that thing. So it's kind of a reward for people who are reading ahead and trying to keep on top of things. Okay. So yeah, so in the bonus I asked you to find the domain of a particular function, and now we're actually going to do a bunch of examples. was the function that I asked him? Maybe it might be. Oh, it was very similar to. It had this in it, but okay. So E. Let me do actually with the guy that was on the quiz, and you guys can see. So this was f of x equals 4 divided by the square root of x squared minus 9. Okay, so we'll do that as well. As some other examples. Okay, let's start with A. So we're finding the domain of g of x. Yes?
Negative infinity. So you do like the regular parentheses, negative infinity, comma, negative 2, close parentheses, because it can't be negative 2, because then the,
Okay, how do you know that? Like, walk us through the law.
because there's x plus 2 on the bottom, so if it was negative 2,
Okay, so this is a rational function. There's an x plus 2 on the bottom, and the
then
problem
it
is.
would equal 0.
Right,
So
so.
then it can't include negative 2. It can go like up to negative 2, but it can't.
Okay, so we said the denominator equals 0, this means x plus 2 equals 0, so x equals minus 2, and then she says, oh, we have to avoid that, right, because you can't do that. And so one way you can visualize this is to draw that number line, and there's a gap at minus 2. And so everything here will work, and everything here will work, but not at minus 2. And how did you write that? How did you write this into?
You do a parentheses, and then negative infinity, comma, negative 2, and the parentheses, and then comma, or right
You do a union,
right, and then
which means or. It's a logic symbol for or. Yeah.
I think negative 2 again, and then comma, infinity, and then
And that's how that would be written. By the way, parentheses, what is the meaning of the parentheses? Yeah?
Well, it's not included. We don't include
This means minus 2 is not included, meaning I can plug in all numbers getting closer and closer and closer to minus 2, but minus 2 itself cannot be plugged in. If I could plug in minus 2, how would I write it? Yeah?
with a bracket.
With a bracket, which is a square bracket. Okay. I want to make sure everyone gets that. So this is how you'd write the domain. This is interval notation. And that would be the answer to this one. Okay, what's the domain of that?
Where the frequencies of each category is exactly the same.
Yeah?
Is it just brackets 2 on 5?
Yeah, domain here is 2, 5 included. Why? F is a polynomial, so it works everywhere, right? So it can work on minus infinity to infinity, but we're given a restriction. Our x must be between 2 and 5. Right? That was listed here. So that is written this way, and because we can be equal to 2 and equal to 5, we write square brackets. So in general, without this information given, the answer would have been minus infinity to infinity, but because I give you that, it's now you have to consider it. You have to consider the information given. Okay. Because this asks you 2x squared plus 5 is too easy. Let's talk about C. Say the domain of H. How do we do that? Yeah.
So the denominator is x squared minus 9 equals 0.
Okay.
And solve for x.
So x squared minus 9 equals to 0. How do we solve for x?
You add 9 over to the other side, so you get x squared equals 9. And then you take a square root of both sides, you get x equals plus or minus 3.
Plus or minus radical 9 equals plus or minus 3. So you should remember that if you're taking an even root, you would get a plus and a minus. Another way to figure that out is to realize that x squared minus 9 is actually the difference of squares. You can write it as x minus 3 times x plus 3 equals 0. And so your x would be 3 or your x would be minus 3. In either case, you get plus or minus 3. In general, as long as it's possible, I tend to prefer you do it this way. There's nothing wrong with that way, but I've seen students forget that they have to change the sign and things. You'll see it a lot nicer in this way. And it also works when you don't have a quadratic, you have other things. The idea in general to solve an equation that's higher than a linear equation is to bring everything to one side, set one side equal to 0, factor the left side, and set each factor equal to 0. Right, so this is a strategy that can work with even larger things, so I would tend to prefer that you do it this way. But either way, plus or minus 3 is going to be the values that are bad. Okay, so now what? How do I use that to get to the domain? How would I write it down? Yeah?
Negative infinity, comma, negative 3 in parentheses, union, negative 3, comma, 3, union, 3, comma, infinity.
Okay. Yeah, that is correct. Just make sure that everyone's on the same page. If you visualize this in the same way, I would tend to, especially if you're just starting out and you're just reminding yourself about how to do this, always like draw a number line and see where you should be. So we understand here that minus 3 and 3 need to be avoided, which means I can be over here, I can be in between them, and I can be over here. So there are 3 sets of places that I could be. There's over here, which is going to be minus infinity to minus 3, not including 3, because if I plug in 3, I would divide by 0. Union, I can be in the middle between minus 3 and 3, again, not including either of them. Or I can be on the right side, 3 to infinity. Okay, so there are 3 sets of equals.
For all values of x, all of these values. And if you well know, not all data looks like that. In fact, data rarely looks like this. Now,
I believe I call that P of x. This was P of x equals radical x over x squared minus 9. Okay, how do we find the domain of that? Ideas. Yeah?
The domain is almost the same as the last one, except for because there's the square root of x on top, no negative numbers will work.
Okay, so how would you actually write that down?
0, 3, 3, positive 20.
So 0, 3, and 3 infinity? Yeah?
There's a bracket before there.
There should be a bracket here, because 0 can be included. Okay, so let's actually see how we got to that. Okay. So notice here, it's almost a rational function, but not quite, because there's a radical in the numerator. So we have to worry about that. It's an even radical, so that has its own restriction. So really what you should see when you look at this is there are 2 restrictions that the function imposes on itself. One, denominator cannot be 0, right? Which means that my x squared minus 9 should not be 0, so my x should not be minus 3 or positive 3, which we found over here. But there's another restriction, and that is because we have a radical. Right, so since we have the square root of x, we also know that x must be greater than 0. So now when you want to put these 2 together to find the domain of this function, again I would start by just drawing a picture where we're going to draw both sets of domains on the number line, and basically we take the overlap. Right, so that's how you're going to figure it out. Okay. So here's our number line. The important numbers are minus 3, 0, and 3. And let's worry about this one. So for this one, 3 cannot be included, and minus 3 cannot be included. But it works here, here, and here, right? Just as we did before. for this one, 0 is included, so I can shade that in. But I need that and bigger. So basically I'm looking for the regions of the number line where both of these lines exist at the same time. If I look in this region, there's only one of the lines. There's only one of the lines. Here they're both of them, here they're both of them. Right, so I need both lines at the same time, so that gives me this region and this region. So this region, notice that the 0 is shaded, the 3 is unshaded, so that is bracket 0, 3, union, and then here 3 to infinity. And that's how we would get the domain. So there are some times when these functions that I mentioned before, we can mix and match them together, and you just have to make sure you look at all possible restrictions that could be on this function. If there are radicals, you need to make sure if it's even, what's underneath the radical has to be greater than or equal to 0. If they're a rational function, the denominator can't be 0, etc., etc. You match up, mix and match all these restrictions, and you can actually draw them on a picture. And just look for where all the functions, a region where all the functions can work. Questions on that one? We had f of x equals, I think it was 4 over the square root of x squared minus 9. That was on the quiz. I think with that example, we don't even need to do the other ones I planned, because it kind of covers those. So what is the domain here?
So how is that going to affect?
What do we need to look out for? What do we need to avoid?
Remember when you have a positive discrete distribution, you have
Yeah?
extremely high.
The radical percent equals negative.
So 1, x squared minus 9 must be what? Greater than or equal to 0. What's another restriction? Can't equal 0. X squared minus 9 cannot be equal to 0, because then you divide by 0. So at the end of the day, we want x squared minus 9 must be strictly greater than 0 for this function to work. Yeah?
Don't 1 and 2 like contradict each other?
No?
Because well, doesn't it say x squared minus 9 is greater than or equal to 0, but then you say it's not 0?
Yes, because we're looking at the two different restrictions. I'm doing the same kind of analysis that I did here.
Okay.
Looking at things one at a time. So when I'm doing this one here, I'm considering the radical,
But then you
right? So I'm saying in terms of the radical, this is what I would need. But in terms of it being a rational, this is what I would need. So I'm doing both at the same time. So how would I know where x squared minus 9 is greater than 0 if I put them together?
You have to solve for x.
How would you solve for x? How do you solve an inequality?
You isolate x, so you move 9 to the other side, and then square root it.
So if you have x squared minus 9 greater than 0, you move 9 to the other side, x squared must be greater than 9.
Yeah, and then you square root it.
It's greater than what?
3. No?
What's good? Can I say plus or minus 3? How would I define that? So let's remind ourselves how to solve inequalities. So for inequalities, the first step you want to do with inequalities, you pretend they're equal, right? So to solve x squared minus 9 is greater than 0, consider x squared minus 9 is equal to 0. right? And for the time being, you pretend that it's an equation, and you want to solve it. So what are you going to get here? We actually found this already. So we know that your x is equal to 3, or your x is equal to minus 3. So there are the two numbers, but how do you know which way the inequality turns? Again, I would like to factor this, and this is another reason why factoring is going to be a nicer method to use it, because it's going to be easier to check what I'm about to do. So you get those two values, minus 3 and 3. And so now what we want to do is, we want to check by plugging in convenient numbers. What do I mean? I want to check the sign of this expression, which is actually the sign of this expression, right? By plugging in random numbers in each interval to see which one works. So for example, I can plug in a minus 4, I can plug in a 0, and I can plug in a positive 4 into this. Okay? Now it's going to be easy to see what that gives us if we look at this one, right? Because then we can look at products, right? It's going to be easier to compute each individual value here and realize if we're multiplying the positives and negatives and just watching the signs. So for example, if I plug in a minus 4 for x here, is this negative or positive? It's a negative, right? Would this be negative or positive? Negative, because, right? So here I have a negative times a negative. Overall, it's a positive. And so yes, it works here. Now what if I plug in a 0? Negative or positive? That would give me a negative. Negative or positive? That would give me a positive. Negative times positive is negative, so it does not work here. Move over to here. Plug in a 4 here, you get a positive number. Plug in 4 here, you get a positive number. Positive times positive is positive, and so it works here. And so that tells you the way that the inequality should be turned. And so now you can just say the domain of this guy is going to be minus infinity to minus 3 union 3 to infinity. So when you want to solve an inequality, pretend it's an equal sign, solve for all the values that solve that, and then you literally plug numbers in the in-between areas to figure out, are you getting what you want, greater than or less than 0? Any questions on? So yeah, that was the answer for the quiz. I don't know if anyone got that. Yes, you have a question?
Yeah.
Yeah.
How are you allowed to do the negative because it was a radical, right? So we said it had to be greater than 0?
What's under the radical had to be greater than 0. So not x itself, but the expression x squared minus 9.
Okay.
Okay? So there's a difference between, say, radical x and radical x squared minus 9. The rule for radicals is if it's an even number, the entire thing underneath it needs to be positive. Right? So the x value itself could be anything in this case, but as long as the entire whole that's under the radical is positive. And you can realize here, if I plug in, say, negative 4, I'm squaring it so it becomes positive, and then I minus 9, it's still going to be a positive number. So here, my x value itself can be negative, but what's important is the entirety of the thing underneath it. Any other questions before we move on? So I said here I wanted to talk about piecewise. Something else that was on the quiz, in the bonus. The idea of a piecewise function. these are functions whose definitions change depending on the region of the domain. Being considered. Okay, so we spoke about a function is just a rule that connects two sets. It describes a certain relationship, but sometimes your relationship can change depending on the context, depending on what time it is or where you are. Okay. And so piecewise functions take that kind of relationship into account, a relationship that depends on the context. Okay, so example, f of x equals 1 if your x values are between 0 and 1 inclusive, and x plus 1 if your x values are greater than 1. This is an example of a piecewise function. This is the typical notation. You do a squiggly bracket, and you write down all the possible definitions that your function can take on. And then you also write down what domain that applies to. So as long as you're between 0 and 1, your function just outputs the output value 1. If your function is, if your x input is greater than 1, it will output x plus 1. Let's make sure you guys know how to read this. Evaluate f of 0.5. F of 3/4, C. F of 2, D. F of 20, F of minus 1.
No, I definitely call that. I definitely call that.
Okay. What is f of 0.5? 1. How do you know it's 1? Yeah?
Because it lies in between 0 and 1.
Because 0.5 is in between 0 and 1. So it means that your input follows this range, therefore you take this definition, and you ignore the other one. So it's always just going to be 1, that's the answer. What about f of 3/4? It's also 1. Because again, 3/4 falls in this interval, right? That's 3/4, 0.75 is a number between 0 and 1. What about f of 2? This will be 2 plus 1, which is equal to 3. I know I take the value plus 1 because that's the definition here, and my 2 is bigger than 1. What about f of 20? 20 plus 1, because I take this definition of the function because I'm in this region, and so that's 20. What is f of minus 1? Huh?
It doesn't exist.
What is f of minus 1?
Doesn't exist.
Undefined. Something doesn't make sense, you say it's undefined. I told you what is happening for greater than or equal to 0 up to 1, and for what's bigger than 1, I did not tell you a definition for less than 0. Okay, so you'll say undefined. Right? That input does not make sense how I define my function. Probably one more thing here. Do you guys know about graphing piecewise functions?
Yeah.
So first of all, you need to know how to graph functions in general. What's the idea behind it? How do you graph a piecewise function? What do you think to yourself when you have to graph one? So you draw the function region by region and you use the endpoints to actually help. So one important thing is each part of this function you need to know how to graph on its own. So that's where you start. So for example, if I had to graph y equals 1, just the top function, what would that look like? Yeah?
You have a horizontal line at 1.
Just a horizontal line passing through 1. And what if I had to graph y equals x plus 1? What does that look like? What would that look like?
Y intersects at 1 and the slope is 1 over 1.
Mm-hmm. And so this way? The other way? So it would look like that. Now what you do is you take into account the regions you're defined by, and you use the endpoints to figure out where you should be. So here one endpoint is x equals 0, so you start at x equals 0 and you realize that, oh, my function has to start here. And then what you do is you ignore everything else, just pretend it's not there. The other endpoint in this definition is 1, so at x equals 1, I can be there. And again, I ignore everything there. So I'm really only caring about this piece of the function. Right? That's why it's called a piecewise function. I just care about this piece, ignore the other pieces. Similarly for this one happens at greater than 1. So I'm going to find 1 on the x-axis, mark it on the function, that would be a y value of 2, and I only care about being bigger. I only care about to the right. So I ignore this part of the function. And so now if I want to graph f, I graph both these pictures on the same axes, but I ignore the parts that I don't care about. So the overall function, the graph of f, look like the following. So it's 1 between 0 and 1. And then at 1, it's here, that's at 2, and then it increases that. So that would be the graph of this function. So I graph this piece, which comes from this piece, and ignore the left and right side. And then I draw the right side of this because that corresponds to that. Okay, so you sort of separate the x-axis into the pieces that are defined by the endpoints. And then you graph it based on that. So we'll stop there. When do we stop? 11? 1, 2, 2:15?
Yeah.
We're all having classes back to back. All my other classes end on the 20 mark. I thought we ended up. Okay, all right. Sorry about that. I'll see you guys on Friday. Okay. Cheers.